Welcome to the NASA High Power Rocketry video series. In this video, we'll discuss the structures of high power rockets. Let's start by talking about some of the common materials used in high power rocketry. Cardboard is a very common material in high powered rocketry. Cardboard is used for airframes, centering rings, motor tubes, airframe couplers, and occasionally fins. Many household items made of cardboard, such as mailing tubes, paper towel rolls, and mailing boxes, can be used to make a rocket. Cardboard is relatively cheap and easy to acquire. It cuts easily, can be bonded together with safe, off-the-shelf adhesives, is non-toxic, and cleans up easily. It does, however, have some drawbacks. Cardboard, compared to other materials, is relatively weak and will not handle the flight loads that other materials may handle. It is also susceptible to damage during transport and storage. Cardboard absorbs moisture, so any exposure to water will weaken it. Nevertheless, cardboard is a popular material among rocketeers. Phenolic is a fibrous material similar to cardboard, but it is impregnated with a resin and heat cured. It is much stronger than cardboard, relatively easy to work with using common tools, and creates little irritating dust. Phenolic is used for airframe and motor tube material in place of cardboard when added strength is needed. Even though phenolic is stronger, it does have some drawbacks. Since phenolic is resin impregnated, it requires epoxy to bond, which can be expensive and presents more hazards to the user. Also, phenolic can be rather brittle. Regardless, when used appropriately, phenolic is a strong alternative to cardboard. Fiberglass is a cloth weave of fine fibers of glass that are impregnated and cured with an epoxy or polyester resin. Fiberglass is a strong and robust material. In rockets, it can be used for virtually any structural component. Its strength and rigidity properties far exceed those of both cardboard and phenolic, and it is not brittle like phenolic. For flights with high aerodynamic loading, such as those that approach or exceed the speed of sound, fiberglass is a good choice if construction is done properly. Commercially available fiberglass rocketry components are already formed and cured, but many rocket enthusiasts prefer to buy fiberglass weave as a flexible cloth, impregnate it, and cure it to their preferred specifications. Fiberglass weave is also used to reinforce structural components such as fins, centering rings, and airframes. Although fiberglass is an excellent structural choice, it also has some drawbacks. First, fiberglass is quite expensive compared to its cardboard and phenolic counterparts, and it is much heavier. Fiberglass requires epoxy to bond, and the dust created when fiberglass is cut or sanded is very hazardous, so handling fiberglass presents an elevated level of risk to the rocketeer. Carbon fiber, like fiberglass, is made of fine fibers that are impregnated with epoxy or polyester resin, heated, and cured, but the fibers are carbon graphite instead of glass. Carbon fiber is stronger and more rigid than cardboard, phenolic, or fiberglass. Generally, when a rocket is constructed of composite materials and strength is a major concern, carbon fiber is the best option. When finished, carbon fiber is also aesthetically appealing. People often use carbon fiber for its looks as much as its physical advantages. Carbon fiber is the most expensive composite used in rocketry, and also one of the more hazardous to work with. Like fiberglass, it requires epoxy to bond, and the carbon dust created when cutting or sanding is extremely hazardous. Plywood is made of several layers of wood bonded together to make several plies. In rocketry, plywood is used mainly for the centering rings, bulkheads, and fins. Plywood can be bonded to other woods or cardboard with common and safe adhesives, but when bonded to fiberglass, phenolic, or carbon fiber, epoxy must be used. Plywood is easily accessible, is relatively cheap, and can be worked with common tools. Sanding or cutting plywood creates dust, so that should be taken into consideration when selecting plywood for a project. Often, rocketeers will reinforce plywood with some other composites such as fiberglass or carbon fiber. Although not commonly used as a major structural component such as an airframe, nose cone, or fins, ductile metal is used in certain places on a high-power rocket. Metal U-bolts and I-bolts are used to anchor the recovery system to airframe components. Metal threaded rods are used to hold electronic sleds in place. Some composite nose cones have a metal tip. Metal hardware or special machined metal retainers are used to keep the motor case in place during flight. All of the metal components in rocketry can be purchased commercially, but some prefer to machine the parts themselves. When bonding any component in a high-power rocket, it's important to use the correct adhesives for the materials being bonded. For cardboard to cardboard, cardboard to wood, or wood to wood bonds, The best choice for adhesion is aliphatic glue, also known as wood glue. Wood glues wick into the fibers of the materials being joined, so surfaces should be clean and smooth sanded to a slightly rough texture for the best bond. Wood glues are readily available, are inexpensive, easy to clean up with water, and are generally the safest of adhesives used in rocketry. If used properly, wood glues result in fewer health hazards than other adhesives. For phenolic, fiberglass, and carbon fiber bonds, the best choice of adhesive is epoxy. Since these materials aren't fibrous, it's important to sand the surface to be bonded with low-grit sandpaper and then clean with alcohol or acetone. This creates small scratches in the surface, so when the epoxy wicks into the scratches, it creates a stronger bond. Even though the epoxy is desirable for certain materials, it is more hazardous to use. Epoxy can cause allergic reactions to the skin, and the fumes can be hazardous to the respiratory system and the eyes. As such, it's important to use proper personal protective equipment when working with epoxy. Gloves, goggles, masks, and other respirators are commonly used to protect the skin and respiratory system when working with epoxies. Hardware is the stronger alternative than adhesives. It eliminates the chemical hazards of adhesives, but it may require the use of power tools. Hardware also adds a considerable amount of weight if overused. Many rocketeers use mechanical hardware reinforcement in addition to epoxy or wood glue bond. We've discussed the many potential materials you may choose to use to construct your high-power rocket. As we pointed out, different materials have distinct advantages and disadvantages. You may want to review topics such as density and tensile strength as they relate to the airframe materials when planning your build. Additionally, epoxy offers the opportunity to discuss several interesting and relevant chemistry concepts. When you mix epoxy, you combine two liquids which react to form a solid, very strong plastic material. Although the final chemical equation for the epoxy reaction is a bit complicated, it begins as four very common chemicals: propylene, chlorine, acetone, and phenol. Here's what the process looks like. As you can see, propylene and chlorine are combined to form epichlorohydrin. The resin and acetone and phenol are combined to form the hardener bisphenol. Epichlorohydrin and bisphenol are the two liquids that you mix together to form your epoxy bond. The chemical formula for the final reaction is this. As you can see, this is beyond the scope of most high school classes, but could provide learning activities such as balancing the equation, identifying various organic structures, and discussing Bronsted acids and bases such as sodium hydroxide. Additionally, when the resin and hardener are mixed, the mixture often gets warm or hot, sometimes extremely hot to the touch. With caution, this could be used in a demonstration of an exothermic reaction. Please remember, safety should be your #1 concern in any activity you conduct with your class. Working with epoxy has many hazards, and great caution must be taken to ensure the safety of your students and yourself. Please review all material safety data sheets and discuss safety with your class before handling epoxy or other dangerous chemicals. Thank you for watching the NASA High Power Rocketry video series.